I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Dr. Taylor Sparks at the University of Utah's Material Science and Engineering Department, and I'm joined as always by my co-host, Andrew Falkowski. Andrew, how are you?
Doing pretty well. Finally feels like fall. I think yesterday was the first day of true fall. From what I can see, there's that crispness in the air that just only comes during this season.
I can tell because I ride a motorcycle to work and the number of motorcycles is plummeting. It's cold in the morning. People don't want to do it. So Andrew, another awesome thing about September, right? Not only are the leaves changing and it's beautiful, but there's another beautiful thing about September, that it is the birth month of sapphire. Now, I had a chance to learn about sapphires when I was in Istanbul a couple years ago and met the wonderful Mubashir Mansoor and his siblings, Maya and Miriam. Mubashir's on the call with us today. He's going to tell us all about gemstones, not just sapphires. Mubashir, how are you doing?
Thank you, Professor Sparks. I'm doing great. It's so good to be here with you and Andrew. Thank you so much for bringing me in.
Well, we wanted to do an episode on gemstones, and we were talking about it. I was like, dude, I've got the guy. I've got the guy. He knows everything about this. I'm sure you'll tell us about the research and actually now the work you're doing in this field. But maybe get us started, Mubashir. When we talk about gemstones, all of our listeners know what these are. We've all seen wedding rings. We've all seen gaudy jewelry. What are gemstones? What's the origin? Kick it off for us.
So gemstones are one of the most fascinating marvels that I have ever encountered. Well, that's why I do the research on them, right? But it goes back to such a long history that we don't really know where it started. In fact, when we go back to the tales of millennia ago, we still find gemstones and the lure that they had to the local populations. So I don't really know when it started, but I think it is as old as time. One of the things that has always made me quite wonder about gemstones in general is how they appear in different legends. And there's a lot of scientific connotations to those legends, but it just was very miraculous at the time. So, for example, there is this very interesting example of the Icelandic spar, which are just calcite crystals. And because in the Viking world, it used to be extremely cloudy when they were doing the navigations, they couldn't really look into the directions unless they had a clear view of where the sun is. But if it's very cloudy and you have very diffuse light, you wouldn't know where the sun is, right?
Oh, yeah, makes sense.
So they had these, exactly. So they had these crystals of calcite, which can be extremely anisotropic. And by having several of these crystals with different orientations, they could kind of get a very good idea of where the sun is because of the polarization that these crystals cause.
No way. And that's so
that
cool.
That was miraculous. So imagine you have these crystals and they can tell you where the sun is in a sky that is otherwise impossible to see, right?
And how back then it would have being considered like a magic, right? Almost like
exactly.
This would have been, they obviously didn't understand the mechanism whereby it worked, but it was clearly important and it gave them value.
Exactly. So from these, there were many of these similar stories when you go back in the history. And all of these have kind of created this legendary tales of gemstones being used for healing, for navigation, for all sorts of superpowers, which are just supernatural. And that's why they exist in all of the different civilizations, in many forms, depending on what kind of gemstones people were able to find in their local environment. So, for example, in the southern part of the present-day United States, many of the Native American tribes they have had these very close connections to turquoise because it's native to Arizona. And there are similar legends that go to turquoise for his healing capabilities and so on and so forth. So it goes the tales of gemstones never really end.
Yeah. So gemstones is a really big category, right? I think our listeners, when we say the word gemstone, they're probably thinking diamonds, for example, or, different colored gemstones. But turquoise is not that, right? It's not a transparent material. So it's broader than just the optically transparent materials that might be colored. It encompasses other things, even metallic ones. It's a broad field, but there's some general families that exist in this, right? So we've talked about sapphire, for example. Do you want to describe some of the broad families of gemstones that are out there?
Oh, sure. So generally, to be honest, there is really no exact definition of gemstones from a materials perspective. What do I mean by that? Gemstones can be completely amorphous. They can be completely crystalline. They can be transparent. They can be opaque. They can be alloys. They can be ceramics. They can be anything. But there are just several aspects that make them special. One of them is that they should be durable. And by durable, we mean they should have some level of hardness so that they can withstand that level of wear and tear that comes with time. And also, you want to have something special, right? So a gemstone with its supernatural, quote unquote, capabilities cannot be something that is readily available. So it has to also be rare.
Yeah.
So it comes with a multitude of those characteristics. It has to be rare, it has to be durable, it has to have some level of beauty. Because at the end of the day, we want something beautiful, right?
Yeah.
But beauty is in the eye of the beholder, so it can be opaque.
Yeah, hence why some people might value turquoise and others might value, lapis lazuli or whatever else, right?
Exactly. So when it goes back to the different gemstone material that are very widespread, everything from quartz, which is relatively more rare compared to the other material. However, it is 70% of our planet is silicon dioxide, right? So it is rare, but it's not really that rare from a chemical standpoint.
Well, so you're saying that quartz, the gemstone, and I've seen these, they're beautiful, like geodes and stuff are oftentimes quartz.
Yeah.
You're saying that's rare?
So rare compared to sand and other types of it's not rare as a sapphire or as a diamond or as an emerald, but it's rare compared to our other material that people are rocks that people could come across, right? So from that standpoint, it has that allure to it, and therefore things like amethyst, citrine, which are just different colors of quartz, have kind of become extremely sought after gemstones, which are used by everyone nowadays. But of course, the super duper gemstones, which are nowadays extremely, relatively a lot more rare, a lot more expensive, a lot more used in the present day, are sapphires, rubies, emeralds, diamonds, taverites, tanzanites. But these are all really interesting single crystals. So, for example, when we say sapphire or a ruby, they're both just aluminum oxide, which is in single crystal form. And then the different colors come from the different dopants that they may have in solid solution. So if it's chromium, then you have a ruby, or if it's a blue sapphire, you would have a titanium and iron in your sapphire as a solid solution. Or if it's an emerald, it would be beryllium aluminum silicate with some little bit of chromium in it.
And it's not just limited. What was kind of interesting in preparing for this episode is sapphires particularly, they're in the corundum structure, so it is aluminum oxide, but it's a specific structure of it. And it's not just limited to the blue or the red. As you had mentioned, there's a whole spectrum of different colors that you can get with them, like even yellows, greens, pinks, depending on the concentration and mixture of those dopants.
Exactly. And also, there's something that we have to note here again. So sapphire or rubies, these are relatively recent. It's not very old that we come across this terminology that sapphire is an aluminum oxide, ruby is chromium-bearing aluminum oxide corundum structure. In fact, when we go back in time, the gemological identification of these was quite a challenge. So back in the history books, or some of the older artifacts that are found in the museums, and they're called, for example, a ruby or a sapphire, they're not necessarily the same material that we call them today. So in the past, any red gemstone that was transparent was called a ruby. So for
So
that
even though you
reason,
could get like a spinel, for example, can also be red,
oh yeah,
they might have mischaracterized that as a ruby, you're saying?
exactly. In fact, there is this crown jewels in the UK, the Black Prince Ruby,
Yeah,
which
yeah.
is a massive gemstone in one of those crowns. It's actually a spinel.
Oh,
It's a red spinel, but it's called the Crown Prince Ruby, right? So the Black Prince Ruby.
well, that makes sense, right? Because crystallography, we've done an episode on it, right? If you go way back in our catalog, it was really only the turn of the 19th century, right? Or 20th century, I mean. So it's only about 100 years old. So it makes sense that they didn't have the tools necessary to define the structure and know exactly what things were. They were using the tools available, which was hardness, which was color. You could look at faceting, but it was pretty limited compared to what we can do now. So I guess that makes sense.
Well, even now, just from some of my reading, our ability to adequately characterize these is still somewhat recent because most of these dopants and chromophores and things that are giving it color are in like parts per million levels. And so being able to determine even like the active sites and their concentrations in specific detail is still somewhat recent.
Let's talk about these defects. Like if like corundum, our listeners, like we've done episodes on ceramics. Corundum aluminum oxide it's a high-tech ceramic. We use it for plates. We use it for all sorts of things. It's an amazing material. But I'm guessing most of our listeners wouldn't have thought that it was a gemstone. What makes it a gemstone is basically two things, right? Is what I'm hearing from you. For one, yes, it's the single crystal lattice, right? The fact that it's not a bunch of polycrystalline grains that are sintered together, but it is one crystallographic orientation all the way through. And the second is the defects. So the lack of grain boundaries is going to give it optical transparency. Otherwise, full of grain boundaries, you're going to get opacity. It's going to scatter light at those boundaries. But the defects cause light to scatter in specific ways. You want to talk about defects and what types of defects we're talking about in these materials, Mubashir?
So when it comes to sapphires or diamonds or any of these transparent gemstones, the point defects are super important. Okay, so imagine you have a diamond structure which is perfectly pure and pristine, and it's just a bunch of carbon sp3 bonds in a huge lattice, right? This is really not that interesting in terms of colors or material properties because it has a huge band gap. The band gap is 5.5 eV for diamond in that case. So for sapphire that is perfectly pristine aluminum oxide and corundum structure, the band gap is around 9.5 eV. So in these structures, I mean, the light would just pass through, right? And we wouldn't have any kind of a interesting optical behavior. However, when we get these point defects included, we have these we have a huge number of possible optical transitions that suddenly appear based on the dopants that we induce in the material. So with them comes a great deal of characteristics, including color. So for example, the color of diamond can range anywhere from very nice pastel pink all the way to yellow and all the way to brown, just by changing the kinds of defects that nitrogen causes in diamonds. So you can go all the way from pink diamonds, which are NV-based, to brownish colors, which are nitrogen vacancy, hydrogen-based. And now the interesting part is, okay, if it's all about those defects, we can always have some kind of a transformation of these defects and then create the colors that we really like. And that is one of the frontiers of the world of gemstones, which has always baffled me.
So when I teach courses on defects, right, I remind them that in ceramics, defects come in pairs because ceramics are charged structures. You have anions and you have cations. So if, for example, you take away a cation by creating a vacancy on the cation site, you necessitate the creation of some other type of compensating defect. You either have to add an impurity where you have like an interstitial additional positive charge to make up for that missing positive charge, where now you've stuffed a positive charge somewhere in the lattice. That's less common because interstitials really crowd atoms. More commonly, you're going to end up with a vacancy on the anion site, right? So they come in pairs. And you know that's not necessarily the case with metals. I'm curious, what's the role of the pairs of defects? Do they interact with one another to give you the color, or are they independent of one another?
They sometimes do. So, for example, in the case of blue sapphires, it's all about intervalence charge transfers. So it's not about it is about very much compensating defects, and it's not just a single defect causing the color by itself. Um, but it's also more than that. So it's the color, the combined color that we see in a gemstone is usually about the ensemble of all of the defects in the crystal combined. So it's not about a particular defect by itself producing
Okay.
color, let's say X, but maybe that particular uh, defect is causing absorption in a particular wavelength, and then you have another absorption caused by another defect, and then another absorption by another defect, and it's the aggregate effect of all of those defects in the crystal that create those optimum colors. And right, so it's always about the ensemble of the defects that are available in the gemstones. Now, it's not just about the color, because when you have these variations in the ensemble of the defects that are created either by nature or by us in the lab, you also change the material's magnetic properties. You also change how hard they may be to some extent. And for example, diamonds, which are very rich in hydrogen, are a lot more difficult to facet and they're harder than the diamonds that are not that hydrogen rich. And this is to the extent that when we grow diamonds in the lab with the chemical vapor deposition method by CVD, we just have a hydrogen plasma, and then we bring in methane gas, and the hydrogen plasma kind of breaks the methane, and then we have a seed crystal, which is diamond, and then on top of which we do epitextual growth of the carbon atom, just building up the diamond, beautiful diamond lattice, and they just follow the structure of the seed crystal that was placed. But since this is done under a hydrogen plasma, a lot of hydrogen gets into the crystals just inevitably. And those diamonds, when we want to facet them and we want to shape them, they take about 50% longer time than the natural ones. So lab-grown diamonds are actually harder from that standpoint.
So is that, I mean, I'm always fascinated with sort of forensics and sort of figuring out truth from false, right? And so when it comes to like true like natural diamonds versus synthetic ones, is that a testing measure that you do? You'll actually explore how easily it facets. I guess that's a destructive technique, so maybe they don't do that. How do they tell, other than the mechanical properties, whether something was grown in a lab or not?
So you're absolutely right. It would be extremely difficult to tell them apart if it was just by this mechanical test, because even we're talking about a material which has a hardness of 100 gigapascals, right? So the main characteristic that we always look for, again, comes from the optical properties that those defects induce in the material. So natural diamonds, there was a time when we could go to a jeweler and we could show them a gemstone that we have, and we would ask, they would just use a simple loop, a jeweler's loop, or the most sophisticated jewelers would have a benchtop microscope, and they would be able to tell apart the natural ones from the lab-grown ones. However, things have changed a lot, and nowadays it's not like it was 30 years ago when the man-made material were so different in terms of how they look under a microscope, the inclusions that emerge because of the processing parameters, and the colors even were quite different at some point. But nowadays, I mean, there used to be gas bubbles and curved striations, and nowadays those days have long passed. So the only real test that we have for diamonds, especially, is spectroscopic. So we actually look at the photoluminescence peaks of the point defects.
Yeah, I was going to say
that's the naturals are causing versus these synthetic ones, the man-made ones.
So for our listeners, spectroscopy is a big field. I'll just say that it's broadly speaking how light interacts with matter. And you could be measuring whether light reflects. You could be measuring how much reflects, how much it transmits through, if it absorbs with a certain frequency. If there's there's UV vis spectroscopy, and there's also FTIR, where now you're looking at Raman spectroscopy. And what you just said is different. That is photoluminescence. You want to describe what is photoluminescence measurements?
So when we have So the way we do these spectroscopic the photoluminescence measurements is we have lasers with different wavelengths, uh, which we use to excite the defects in the material. And once we excite those electrons with the higher energy of our lasers, they have some naturally some natural wavelengths of light which they give off. And it's characteristic. So each defect has its own characteristic interaction with that laser light. And then we kind of record that in the kind of light that they emit and the phononic vibrations that they provide. And it's the combination of the both that gives us a very
Gotcha.
clear idea of the kind of defect that is available in the material. So
So I'm curious how that can be used to then differentiate if the same dopants. So for example, if I'm a synthetic versus a natural ruby, will have the same chromium centers that are the chromophores. So how are you differentiating them? When I was just doing some looking online, what I had seen was there's a lot of different growth patterns, and that's usually the determiner. But it sounds like you can also do this with photoluminescence. So how does that work?
So, for the case of rubies and sapphires, you're absolutely right. It is usually not the photoluminescence, but the growth patterns and
I see.
the microscopic examinations that do the work. Because in in um, in diamond, you can get a very clear image of the point defect landscape just through photoluminescence spectroscopy. But in sapphires or rubies or emeralds, that's not really possible. Um, so yes, in those gemstones, you really rely on the growth features and the inclusions that somehow get into the game. And if it gets too complicated, which it sometimes does, you rely on trace impurity analysis. So let's say you were growing your ruby in a flux which is lead rich, and lead is not really found in the nature. And then you would just go on and look for that in your ICP analyses and okay, oh, there's lead, so there's something going on fishy over there. But for the case of diamonds, yes, we do get the same dopants. So the same dopants do cause similar kind of point defects, but there is a catch. So we have a paper that was published in 2019, and we claim that it is impossible for any kind of a growth mechanism. It's just thermodynamically impossible to produce the same defect ensembles that natural material has in the lab. Like, it's impossible to replicate that. And the reason for that comes purely from a combination of kinetics and the chemical potential equilibrations. So what happens is we do get the same defects, but it's not about the relative proportions of those defects. That will always be different. And that's completely because of the speed at which we are doing it in the lab and the speed at which nature does it. So, for example, we can have a lot of nitrogens in diamond, which are just single nitrogen atoms. But in nature, there will be a lot more of nitrogens that are agglomerated together, as in aggregates of nitrogen, like a nitrogen 3 vacancy center or nitrogen 4 vacancy center. And there will be a lot more of those compared to the ones
Interesting.
we
So it's like the local structure of the defect. Even if the concentration is the same, it's how they might group, cluster, and how that cluster might interact. Wow, that's really sensitive. Maybe even a harder question is, I know it's possible in some cases you can actually trace gemstones that are natural, but from different origins. You can actually do provenance testing, right? I know I've seen your social media and stuff. You're always traveling to Sri Lanka and these places. How do you know if a gemstone comes from one place versus the other, assuming that, other things are sort of equal?
That's again, it goes back to the trace impurities, because the geochemistry of each mine is unique to itself. And the material that is, for example, mined in Sri Lanka will have its very own trace impurities of gallium and proportions also of chromium, manganese, magnesium, and so on and so forth, even if it's just ppm level. And that is kind of unique for each mine. So there are databases which places like the Gemological Institute of America and other places try to accumulate by going to these mines, sampling, and trying to figure out and trying to create a map of which kind of trace impurities would be common. But there is an interesting catch to this. A few months ago, I was in Sri Lanka. There is this mining village, which almost most of the sapphires in Sri Lanka are found from. And they were talking about this new deposit, which was a little bit further away, that had puzzled some of the huge labs. So people were actually paying a premium for the material that was coming from that mine, because when it was sent to do origin determinations to some of these larger labs, they were getting certification that this material was from Kashmir and not Sri Lanka.
And they're like, no, that can't be right.
Exactly. Yeah, but that really shows it's like the database did not have that information, right? And it kind of just resembled the ones which were coming from Kashmir. And Kashmir material sells for a premium. So all of a sudden, that material was selling for a premium because it was similar to the geochemistry of somewhere else. Yeah, but that happens a lot. And it really shows how much of a space the world of gemology has for materials engineers.
I love this because you're saying, materials engineers, like 30 years ago, a dude with a microscope could sort of look at it under and decide real versus fake. But now you're saying we're using high-tech tools, right? There must be a business opportunity for entrepreneuring material scientists who want to get into gem characterization or standardization business, which is pretty slick. You want to tell us a bit about these lab-grown materials? How do they actually grow them? Because obviously, one of the key things for most gemstones is it's got to be a single crystal. And as somebody who's grown single crystals, I know it is a pain in the butt. It is not easy to do. CVD is just one method. You mentioned chemical vapor deposition for growing diamond, but there's certainly other approaches. What are the sort of tools that are used out there?
So people are using all sorts of methods, ranging from melting the raw material. Let's go with examples. Sapphires, we can just melt aluminum oxide at 2000 degrees Celsius, 2050 degrees Celsius, right? So the moment you melt it, then you drop a piece of rod into that melt that is a little bit colder, and you trigger crystallization over there, right? And imagine you have a seed. So that would be growing just gradually over time. So that would be the Czochralski method, growing from the melt. You can also have growing from droplets of molten powder. One of the oldest methods was actually the Verneuil method, where you have a flame and the powder of, let's say, aluminum oxide was actually passing through that flame of temperatures above the melting point of sapphire. So with a flame temperature of around, let's say, 2,300, 400 Celsius. With the melting of that powder, you could have another seed crystal at the bottom of that melt and grow on top of the pool which you're growing on.
Is it from the liquid droplet that it grows, or does it go to the vapor phase and condense?
Just directly from the liquid in case of the Verneuil. And the Czochralski method kind of came after this, where you had larger sizes. But nowadays, people can grow single crystals of sapphire, which are 80 kilograms in weight.
How big?
So 80.
Kilograms?
80 kilograms.
That's massive.
Yes. Huge.
That's more than I do.
In fact, there was this contract between Apple and GT Technologies, where they were trying to do Apple glasses for the iPhones.
Yeah.
Made of sapphire, but they just couldn't do it on a large scale. But yeah, technically it's possible. I mean, from a scientific point of view, there is no problem. Maybe some engineering problems.
Oh, way cool. I see you mentioned earlier that they can grow them from flux. Just for our listeners, because I didn't know what this was for the longest time. If you think of a phase diagram and you think of the regions where there's a liquid and a solid present, right? These things can be, and you've done the lever rule probably if you've taken a material science course, you know that the ratio can be tunable. Essentially, you grow it intentionally in this liquid plus solid region where you don't care about the liquid. That's your flux, right? That's the thing that you don't want in your gemstone. But the gemstone is the solid that grows in that region. And so as you control the cooling, you can actually grow these things fairly large and you can get single crystals out of the flux. I think they're a lot smaller than Czochralski. You're not growing 80 kilogram things, but you can grow crystals, at least at the academic research scale. These things are millimeter scale. You can grow those pretty easily using flux methods.
Well, I think the big ones aren't grown with Czochralski.
How do they grow them?
I think they use some sort of heat exchanger or hydrothermal synthesis. Is that correct?
Yes, exactly. So for the 80 kilos, they use the heat exchanger methods. You're absolutely spot on. But even for the Tchaikovsky, the crystals are not that small, so they can be at least 5-10 kilos easily.
Jeez.
But the good thing about the gemstone world is that 5 millimeter is large.
Yeah, right.
So, the flux method is good enough for creating really nice gemstones. And for example, the earliest rubies that were made in the lab were through the flux method, and they were using combinations of cryolite and lead fluorides and those kinds of fluxes, where with them the alumina gets, so you have a eutectic with the lead fluoride or cryolite and alumina, which is around 1000 degrees Celsius, 1200 degrees Celsius. So it's possible to grow these crystals with a very simple kiln, with the right chemistry, if you don't mind a little bit of a lead vapor in your room.
Yeah, a couple of years ago when I was visiting you, Mubashir, and I was on sabbatical, I got an email from one of my entrepreneuring students who was, I don't know why he was messing with this, but he'd grown a ruby crystal out of a lead flux. And I was like, all right, first off, that's awesome. Second off, why are you doing lead in my lab? Like, that's not something we're keen on working on. So, yeah, very cool.
I would have definitely sent that to Gemological Institute of America or something to mess with them.
Yeah.
You know why? Because every single growing technique, which comes out of the process, so with variations in the process, the gemological knowledge just gets quickly extinguished. What do I mean by that? The world of gemology. So gemology is the science of gemstones, right? It's a extremely multidisciplinary subject, which brings in science, everyone from solid state physics to material science to geology to economics, arts. It is one of the most fun places to be honest. I really enjoy working with gemologists because it's just such a widespread community and extremely multicultural in the different fields. But when the way it works is, it is extremely based on statistical analysis of the material that is available in the market. And gemologists don't necessarily do the synthesis or the heat treatments or post-processing of the material. They are just more on the forensic side of things. And with that comes a huge problem, and that is which material scientists can solve. And that's why I'm talking about this here. The problem is when it comes to the forensic side, when we rely on material that is available in the market, the moment something new comes up, the moment some new heat treatment, some new production process appears, then we kind of lose it completely. And there is really no database on top of which we would know what's going on. Huge potential for materials engineers there. Because imagine if it was the other way around. That's why I always keep hoping in the world of gemstones. A day where materials engineers really look into this side of gemology. Because even the more fun part is, most of the history of gemology has not been built by the gemologists. It has always been through some physicists who got really interested in the field and came in and did real contributions, usually after their retirements, or someone from a totally different field coming in and contributing. So we really require contributions from material scientists a lot.
Yeah.
For any aspiring materials engineers out there, please look into this field.
Yeah, it's really cool, especially from a material science standpoint that you mentioned. It's always fun to find these industries that are kind of like this. Tangentially, coffee is a lot like this too, where
totally.
It was very much just driven by people who were messing around with things. And it's only really in the past, probably 10 years that scientists have actually started to look at coffee and try to understand how complicated of a chemical extraction process it is and start to dial things in. I make espresso every morning, so I'm very familiar with the market for that, and it's only within very recently that temperature control, pressure control, and profiling really came onto the scene. And it sounds like that's very similarly the case with the gem industry as well. One thing you had mentioned that I wanted to circle back to is this idea of heat treatments and post-treatments to the gems themselves. I know that for a lot of different things, you can enhance the color and improve the clarity through heat treatment, but it's more than that too. Like emeralds, for example, are liable to crack or be found with cracks in them, and they can even infuse those and diffuse like glass into that to try to heal those cracks optically.
Oh, cool. I didn't
Can
know
you
that.
talk a little bit about some of the other things that they do to treat them and why they treat them?
Exactly. In fact, your example of coffee is really spot on, because when I go to Sri Lanka, every now and then I come across these extremely old techniques. So Sri Lanka is special because they are one of the cradles of sapphire trade, and also they have a very long history of sapphire mining. But you always come across these gentlemen who have a blowpipe made of bamboo, and they have some amount of charcoal. And with the combination of the speed at which they're blowing into that pipe and heating up the charcoal fire and keeping the gemstone in, they're able to tune the color of the gemstone and enhance it. Now, the fun part is this is an age-old method. Today, people are able to do it a lot better if they do a more precise temperature control, a more precise pressure control, atmospheric control, etc. But it comes back to the same principles, where people are changing the point defects in the materials, and then they are able to get enhanced colorations or enhanced clarities by dissolving some impurities in the solid solution. Now, why it gets interesting is not just the value addition part, but also from a technological standpoint. At the end of the day, the whole process is about changing the material properties through some kind of a process. Isn't that really the definition of materials engineering?
Yeah, absolutely.
Exactly. So heat treatments of gemstones in the gemstone world, in the gemstone industry, are looked at as this mystical processes which come through generations within a single family as this huge trade secret, which only a few families know on how to do it perfectly. But the problem is, only a few families know it, kind of in a so-so manner, because it is not really looked at from a scientific standpoint. And when that's what exactly we're trying to do. So we try to focus on what kind of point defect transformations they're triggering and how we can do it even better in a more optimized manner, in a more optimized and controlled atmosphere. Because at the end of the day, 90% plus of the material that is mined is not that useful as a gemstone. Even if, let's say, we go to a sapphire mine in Kenya and we come together with the miners, the majority of the material that they will show us will not be really material that a jeweler would like to use. But that miner has to be able to make a living, right? So you would want to, the idea is you would want to have a maximum amount of material that could be made useful so that the mining process could become sustainable. So heat treatments are extremely essential for the backbone of this industry from a mining standpoint. So it's not just about making a few bucks so that you can increase something's value. No, if you don't do these heat treatments, you will lose all of the
like the
material
mining
that is actually mined.
Yeah, the original mining no longer is profitable without some way to use this additional. Yeah, I love that.
Exactly. Absolutely. And the most fascinating part is doing it from a scientific standpoint. That is so lacking because we really have no idea in the world of gemology what kind of defects are responsible for the majority of the heat treatment transformations. So believe it or not, even now, when you look at sapphire heat treatments, the literature on heat treatments of sapphire is very much non-existent. So we will find a few papers, which will be less than 10, probably, which really go into the science of it, and that's it. Now, it's a pity because the only reason this is happening is because we don't have. So if we were to draw a Venn diagram of gemologists and materials engineers, and in that intersection of that Venn diagram, the union is kind of like maybe
A
three
sliver.
people.
Yeah. Yeah.
Exactly.
So, Mubashir, you've got a new company. It's STEMZ, right? So STEM, science,
Exactly.
technology, engineering, and then for Gen Z. And you're using Gemstones as a platform to connect these STEM principles to Gen Z audience, right? What exactly are you doing? It
Exactly.
has to do with gemstones and heat treatments, I believe?
It does. So we kind of are defect engineers, and it's been a very interesting journey because it started as defect engineering for the world of gemstones, but we quickly realized that the world of gemstones are so complicated, and the defect transformations that you have to induce in material require such a deep level of understanding at materials uh, atomistic scale
Yep.
that when you grasp that, you can kind of apply the same principles to a whole lot of other materials as well. So we kind of started from this platform of gemstones and gemology, but we quickly escalated into well beyond. So we are now doing the same principles of defect transformations to do better batteries, to do better capacitors, to do optimized 2D materials, and you name it. But it all started from the love of gemstones.
So cool. Well,
Thank you.
before we wrap up, there is a topic I want to transition to. If you've seen the meme, there's like the low IQ, medium IQ, high IQ, and the low and the high IQ sometimes agree on things with a really simplistic view. In this case, it might be like sparkly rocks are important, right? And why would sort of like the technologists out there be worrying about the potential use of gemstones? You're like, all right, yeah, they're beautiful. We put them on our wedding rings. Is there a technological use for these? There is, and it's one you pointed out to me. Tell us about these diamond color centers and what role they may play in quantum technology.
Okay, so what really excites me about the future of staying in the world of gemology is really not the bling for me personally.
Although
But
it's awesome.
it is awesome for sure. But it is the bling which goes in the world of technology. So, for example, the quantum computing world. Uh, Nowadays, people are trying to build quantum computers with cryogenic temperatures, all sorts of refrigerations and millikelvin temperatures by using superconducting qubits, right? But there is an alternative, and the alternative, and those technologies are not cheap. So I was in Delft a few days ago, and there was this company who was creating these super cool fridges for these millikelvin temperatures, and a very small one for a lab scale setup costs something like $500,000.
Yeah, they are crazy expensive.
Extremely expensive. So that really says it all. I mean, we can't transition those technologies to a everyday laptop, right? However, diamonds are the platform on which we can have room temperature quantum computing.
And this has already been demonstrated, right? You can
It
have
has been.
specific types of defects. They call these NV centers. I remember when I was at grad school 15 years ago, there was a team down the hall. This is like all they did. And I was like, color centers, NV centers, and diamond. What are you guys working on? Because I didn't have the vision yet. I didn't understand quantum computing. But essentially, that defect pair, so diamond has a big old band gap, right? 5.5 eV, you said. But this defect now exists in that band gap where you can get an unpaired electron, right? The nitrogen adds this electron, which is now an unpaired electron. So this can have spin, right? And it can have a superposition of spins. And this is now a controllable defect, right? You can hit it with light and it can do single photon emission, for example. This can act as a qubit, but it's stable at room temperature.
Exactly. And it's the super fun part is now we are coming to the point where we can actually build these NV-based diamonds with extremely well-tailored architectures. So imagine we can have NVs in any kind of orientation and any kind of ensemble that we may want. And that was what really lacked 15 years ago. But now things in the diamond growth world are going there. So this really comes back to the point of if we are able to go a few steps ahead, it would become extremely probable that we can have these quantum computers at room temperature thanks to diamond and defects in diamond and the color centers of diamond.
And again,
But it doesn't only stay there.
And one of the reasons why diamond, you might be like, well, diamond's so expensive. Why do I have to use it? But it is those characteristics of diamond that allow these defects to be so stable, right? Diamond is an incredibly rigid lattice, which gives rise to its hardness and its optical properties, but also makes these things stable. I think they have coherence in like millisecond scales at this point now, right? They can, which is short, right? But it is way longer than what you could achieve otherwise, especially at room temperature.
Absolutely. Now, it doesn't only stay there. So, for example, nowadays, people are using the NV Center for magnetic sensing. They're using it for pressure sensing. They're using it for even something a lot more cool. Imagine you have a nanodiamond. And the nanodiamonds, so NV can come in different charge states. So it can be neutral, it can be negative.
Okay.
And the charge state of the NV, each charge state will have a different photoluminescent property. So it's basically, if you can somehow create an environment which changes the charge state, since the photoluminescence side of things change as well, you can use this as a sensor.
I see. So what sort of things change the charge state?
Any kind of adsorption on the nanodiamond changes it.
So this becomes like a chemical sensor or what?
It does, exactly. And people are using this for sensing some molecules, including gases, drugs, and all sorts of things. So people are even using it for controlling the adsorption mechanism in a controllable manner. So imagine this. You have a platform where these nanodiamonds act as a sensor, and just by changing PL ratios of the NV zeros and NV minuses, you have calibrated a system. So it's the same color center that gave you pink diamond can also give you really cool sensors.
So cool.
And that's really how it transitions from classical gemology and gemstone to state-of-the-art sensing devices. But it doesn't end there. The most fascinating diamond electronic that I have ever heard of is the one which was made by the group of Professor Prower in University of Melbourne. They made a clinically blind person see again through a diamond-based sensor that does the job of retina, and it does it because of the of just the N-type and P-type doping in diamond that is again made possible through defects. So I think the Australian government spent something like $100 million on that project, and it is one of the most successful diamond-based electronics because it was clinically done, proven, and it has got things even going further ahead. So
dude, I'm looking that up right now. That is wild. We will put a link to that in our show notes. That is so cool.
It is. It's really awesome. But it doesn't end there. So we were talking about sapphire just a while back. Sapphire as a awesome gemstone, but also sapphire is one of the most fascinating lasers. So chromium bearing corundum, aluminum oxide, it is a laser. Titanium bearing, it is a laser. So all of these defects that in the world of gemstones provide these awesome colors are also at the same time these superb materials that could be used for advanced technologies. And that's really the link which has always excited us, because when you're doing these kinds of research, you are both in touch with that glamorous world of gemstones and super luxurious lives of these aristocrats of our world, but at the same time, I kind of feel like a Robin Hood, because by making some money there, you can go on and do your awesome technology.
I love that. Well, Mubashir, it is always a pleasure. It is a joy to be able to chat with you, man. I hope we get to see each other in person again soon. I need to make a trip out to Istanbul to see you and your wonderful family. But thanks for joining us on the show today. We appreciate it.
Thank you so much. Thank you. I really appreciate the conversation today. And I look forward to a lot more on the subject in the future when we have our own super crazy crystals growing in the lab.
Give us an update in a year or whatever it is from now. We would love to hear what you've accomplished. So we will wrap up. We do want to point out a huge gratitude to our sponsors. American Ceramic Society has sponsored this episode. You've heard us talking about them. They're great. I actually just finished last week teaching my online course, right? They have their Acers Learning Center with on-demand courses. I taught about felt refinement. You can check it out. Even if you weren't able to be there in person, you can watch it after the fact. That's the whole benefit. And we have a couple other ones to promote this week. Orton Ceramics, right? Orton Ceramics has partnered with the American Ceramic Society to put a bunch of courses available focusing on refractory ceramic materials. So they've got a course on advanced thermal properties of refractories, another one on design and failure of refractories, and even like refractories fundamental if you're like, I don't know what he's talking about, right? These would be great resources to sort of upskill yourself, become a better employee, especially in the world of refractories. And best of all, because they've partnered with our show, you can go to ceramics.org/materialism and get $100 off your next on-demand course registration. So please do it. I think you'll enjoy the experience. You'll learn a lot from it.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialismpodcast on Instagram, or pretty much everywhere you want to find us. We are out there and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, AlphaBot and Kolobite. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.